Hello Info-Person, this is Anton, and in this video, we're going to be discussing a somewhat unusual discovery in astronomy. An object that's a little bit difficult to define, even though technically we should be referring to this as an exomoon, or basically a moon of an exoplanet. Something that astronomers have been looking for an extremely long time, but something that was naturally extremely difficult to see, because by definition a moon should be smaller than a planet. And we're only now getting better at seeing planets and detecting them in various star systems. And so for many years astronomers have been hunting for this first official confirmation of some kind of an exomoon out there. But despite many attempts and many claims, prior to this discovery we're going to be discussing today, we didn't actually have any official confirmations for the existence of exomoons out there, even though based on what we see in the solar system, we kind of assume that exomoons should be all over the place. But because they're so small, we only had candidates and nothing confirmed so far. However, a recent study that was just published in the Nature magazine has finally revealed something that may be a breakthrough in the exomoon research. But it just turned out to be much weirder than anyone expected. And so in this video, we're going to be discussing this study by Kevin Hoy and the team you see on the screen that almost definitively confirms the existence of an exomoon 73 light-years away from us that seems to be orbiting another object. But here's the catch. The object it's orbiting is not exactly a planet, and the moon itself is not at all similar to our moon. It actually seems to be Jupiter-sized. And so the big question from all of this is, of course, when is a moon not a moon? Or basically, how do we even define what was discovered in this study? And so let's talk about the strange case of CD-352722 and discuss exactly what was found. But first, before we start, let's briefly discuss why it's so difficult to find these exomoons and what techniques are usually used. And so while we found thousands of exoplanets, hunting for their moons remains one of the most technically challenging frontiers in observational astronomy. And that's because traditional techniques such as Doppler spectroscopy, or basically using radial velocity, is still very difficult because the technique is just not sensitive enough to detect minute motions of the moon. And normally, we only see the gravitational pull from the planet, but not from its potential moon. And while in the past one of the most promising methods was referred to as the transit timing variation, or basically trying to detect extremely tiny variations as the shadow of a planet passes in front of a star that should actually be just a little bit different every single time if there is a moon in its orbit. And that's because a moon in this case would be pulling on the planet and moving it just a little bit every single time. But the problem here is that this shift can also be caused by some kind of a planet that we're just not seeing, like in this case in this simulation. And so using these transits to try to find moons can usually give us a candidate, but not a definitive confirmation. Additionally, a slightly different method relies on the observation of various chemicals in a star system, and specifically one of the candidates was discovered based on what we see on Jupiter's moon Io. Specifically, that tidal heating should actually cause some of the moons to become volcanic, and thus cause them to expel certain compounds that should not be visible from a gas giant. And so, for example, various sulfuric or silicon-based compounds detected in large amounts around some kind of a gas giant could suggest that it's actually being produced by the moon. And though this has also been discovered, it's still a candidate because, theoretically, it could have come from somewhere else entirely. Likewise, by observing Jupiter and Io, we know that these types of systems produce very specific radio emissions. And that's because Io tends to trigger certain radio emissions when Io's ionosphere interacts with Jupiter's powerful magnetic field. And so somewhat similar radio signatures have been found around some systems, possibly once again hinting at the existence of moons. But once again, there could be some other mechanisms producing similar signals. And so time and time again, even though we have some explanations and some potential observations, after years and years of research, so far nothing concrete yet. But things become slightly easier if you actually start to look at unusual star systems, especially the ones that involve really massive objects. And so here let's actually briefly discuss the hierarchical structure of a typical star system. And so, for example, in our own solar system, things are pretty simple. We have the Sun in the center, and then we have planets like Earth, Jupiter, and Saturn orbiting the Sun. And most of these planets also have moons, with moons orbiting the planets. But in this system, this is actually just a little bit different. it's referred to as a three-tiered system because it's structured in a slightly different way. And so at the top here, we have the primary star. In this case, this is a typical young red dwarf, or an M-type star that's about half the mass of the Sun. So essentially the most common type of a star in a galaxy. But then, orbiting the star, there is actually another object, a brown dwarf. That's technically what you see right here, and it's a brown dwarf known as CD 352722b. And well, sometimes we call brown dwarfs failed stars. That's because they essentially never got to have enough mass to initiate nuclear fusion. But they're still much more massive than planets, with this one being at least 31 to maybe 37 times the mass of Jupiter. But once again, not massive enough for hydrogen fusion. Here it would have to be at least twice as massive. But then there's this new discovery that seems to be in orbit of this object. And so there is an object orbiting the brown dwarf. But the problem is that this is a really massive object, 70 to 90% mass of Jupiter, or basically more than double the mass of Saturn. And so if this was in a solar system, we would obviously call this a planet. But because it orbits something that orbits a star, it seems to behave exactly like a moon, and, well, in essence, technically is a moon. But a moon that's basically a gas giant planet. Which is why the lead author of the study, Kevin Hoy, refers to this as an exosatellite and not an exomoon, essentially a kind of a neutral term that describes an object orbiting a larger body outside of the solar system. And so I guess the first question is, so how do we know it's here and how was this found? Well, because this is so massive, and because this is planetary in size, even though it's 73 light years away from us, here it was not that challenging to find. But instead of looking for transits like we do with normal planets, here researchers relied on the Very Large Telescope in Chile and used the radial velocity technique that essentially looks at the tiny wobbles of the object itself. And so here, by looking at a star, and by seeing very tiny redshifts and blue shifts that happen periodically, researchers can then discover some kind of an object orbiting something else. And technically this is the same method that was used to discover some of the first exoplanets ever found, the pulsar planets discovered back in the 90s. And so as this Jupiter-sized object orbits the brown dwarf, its gravity pulls on the brown dwarf so much that it causes the object to wobble back and forth with a very regular interval. And by measuring the changes in the spectrum and looking at this object for 2.5 years, the team detected a very clear signal, which is what you're seeing here. And the signal shows us that this moon orbits the brown dwarf every 170 days, making this the first time in astronomy that this wobble technique, or the radial velocity technique, has successfully confirmed the existence of a satellite orbiting around a planetary or a brown dwarf object. And here this is a very clean detection compared to previously blurry data, where it was very difficult to determine if a moon is a moon or just some kind of noise. In other words, this data is extremely precise. But obviously, when we see a signal like this, the obvious question is, okay, so can it be something else? Or is there any chance that this is still noise? And maybe something coming from the brown dwarf's atmosphere? And that's because, unlike planets, brown dwarfs do have some extreme activity on the surface, and can even have clouds and weather that sometimes mimics a wobble without an actual object orbiting them. And so in this case, the team performed a very extensive analysis, but actually found no correlation between this signal and the rotation of the brown dwarf or its atmospheric activity. And here they even present us with two possible solutions to this data. One of them involves some kind of a larger object on an elliptical orbit, and the other one involves two separate satellites with a resonant orbit where they push and pull on each other in a specific rhythm. But when they ran computer simulations to see which solution made more sense, and to basically see which of these satellites would survive the longest, the two-satellite version was a mess, but the one-satellite version survived for a very long time. Actually, the two-satellite version only survived for 500 years. And this gives astronomers an extremely high confidence that whatever is happening here seems to be real and seems to involve one massive planetary-sized object. But that also brings us to that definition crisis. So what do we even call this? Now once again, if this was orbiting a primary star, we would just call it a Jupiter-sized exoplanet. But because it orbits a brown dwarf, and because a brown dwarf is a substellar object, here the lines get super blurry because it's not orbiting a planet, but it's also not orbiting a star. And according to International Astronomical Union definitions, an object is a planet if it orbits a star or a brown dwarf, but stays under a certain mass. And so by that definition, this moon is technically a planet. But it's a planet orbiting another planet-like object, making this a very unusual triple hierarchical system. And so researchers here argue that we might have reached the limit of our definitions and our language, because words like moon and planet were invented to describe our own solar system, but seem to not make sense anymore when it comes to these bizarre systems. With this system transforming over time into something else entirely, because right now it's actually pretty young. But over billions of years, this brown dwarf is going to cool down and become dimmer, and the star will also transform into something else. And so the environment where this exosatellite is orbiting is completely different from what we normally have in the solar system, or even in other star systems we've seen before. But here this discovery is also important in order to help us understand how planets and moons form and evolve. And that's because when it comes to planetary formation, a lot of our theories are still incomplete, and this system seems to be a kind of a perfect testbed for studying how gravity seems to create these systems and how it seems to create these multi-tiered examples where an object orbits another object, which then orbits another object. While at the same time, because the technique worked here, we can now also potentially use it in other systems, even in systems involving terrestrial planets that are maybe just a little bit closer to us. And this could be important because a lot of scientists now believe that many of these exomoons could actually be much better places to look for life than planets themselves. Mostly because, just like Io, they can actually receive a lot of heat from tidal interactions and can thus stay permanently warmed up and even contain liquid water, similar to moons like Europa and Enceladus, and thus, by definition, do have a chance to contain life. And so in the future, using various similar techniques, there's a very high chance we're going to discover even more of these satellites, possibly entering the Exomoon era, allowing us to discover hundreds and thousands of these objects, just like scientists did with exoplanets with telescopes like Kepler. And so for astronomy, this is definitely a really exciting discovery. But in the end, it also reminds us that, in general, the universe does not always like to follow the rules that we tend to follow in astronomy. And so even though we like to think of moons as these tiny rocky objects orbiting planets, here the universe shows us that it likes to create objects that do not fit our criteria. And sometimes we get these strange hierarchical systems that are just a little bit difficult to understand. But as we get more data and as we get bigger and more powerful telescopes, we'll probably have even more exciting discoveries sometimes in the future, which means that there will be more videos about this once researchers find something else. But until then, check out previous videos on similar topics in the description below. Thank you for watching, subscribe, come back tomorrow to learn something else, support the channel on Patreon where you can find additional videos without any ads and can DM it directly, or by joining a channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.